Right, well, good evening, everybody, and thank you for braving slightly chilly weather to come and hear me talking about hotting up. What I'm going to do today is take a bit of a stroll around some of the challenges of climate change in the 21st century. Some of you will know this is the second of my lectures this year on global scale environmental challenges, and the first lecture considered new developments in Earth imaging, and I recognise some of the faces, some of you were here then. But there are indeed some amazing things coming out of satellite imagery now that have made us think again and anew about the planet and about our impact on it. The images here show some pictures taken just earlier this year by a satellite called Sentinel-3A. It's a European satellite, and you can see the sea ice being generated. One picture's in June and the other one in August, and you can see the glacier shedding its ice. The point I want to make about this is there's so much data, it's so graphic, and it's now, these days, so immediate. So, today's lecture takes place in the knowledge, a certain amount of knowledge about global temperatures. And the one I want to look at just for a minute is NASA's Goddard Institute scientists who showed the first 6 months of this year to be the hottest on record, and Arctic sea ice now 40% lower than in the 1970s. Now, part of the data used to construct these curves, which go from left to right from January through to December, and these are if you like, anomalies. They're showing the amount of difference from the long-term average as we track across. This is data showing that, as I said, August 2016 was the hottest August in 136 years of record, and in fact it was the 11th consecutive month that such a record has been smashed. Now, I want to show you this representation, which I think illustrates this very, very well. It's a simple pattern, year by year, showing the temperature as it goes around, and this is what's happening. So now we're in the 60s, and we're now in the 80s, and you can see the last couple of years, including the last year, as we're getting very close to that 1.5 degrees centigrade position, about which there's been quite a lot of concern. You can see that last year is indeed a record breaker, and the typical monthly average now is about 0.8 of a degree higher than it was in the 1880s. Now, that may not sound very much, but current thought is that the last glacial period in the UK was only about 4 degrees colder than the recent past, and although it's pretty chilly tonight, we wouldn't want to be there. So small differences in terms of the number of degrees have big consequences for human activity and, in fact, the planet as a whole. As a result of that analysis like that, many nations met in Paris last year, as you will perhaps be aware, and last week the recent Paris Agreement came into force. Many nations agreed to direct their efforts to keeping climate change under 2 degrees and, if possible, under 1.5 degrees. Now, that's an average. And if we use more data, we can also start to see global patterns emerging, variability over space. Now, I couldn't get this one to work interactively, but you can see here tiny maps. So at the top of the map, we've got up here, we've got the 1880s. This is every year going across the 1880s, 1890s, and so on. I just pulled out some examples here of the maps of these are temperature anomalies in the top four corner there. Basically, if it's blue, it's colder than average. If it's red, it's hotter than average. And to think again, you can see the same kind of picture emerging, not universally across the surface of the world, but as you get down to the bottom here, we're seeing more and more red, hotter and hotter, until we get to 2016 down here. Okay, now, if we use... we can tell by our records, again, that most places have become hotter, again, by about 0.8 of a degree. Now, you can quibble with the basic data for this, and people have. For example, you have to make corrections to allow for the fact that more and more meteorological stations are in urban areas because urban areas have got bigger. And when you're in an urban area, it tends to be warmer anyway. So with urbanisation, naturally, the records of the Met stations in those areas tend to show warming. And some correction has to be made for that because it distorts the overall record. But even if you do that, I think the diagrams like this and that previous one probably make it very difficult to deny that the climate is actually warming. Now, of course, one swallow doesn't make a summer. One hot month, or even a series of hot months, doesn't necessarily imply longer-term planetary warming, let alone a human-induced shift. And even though this kind of data was based on 6,300 meteorological stations and ocean surface temperatures taken from satellites, it only demonstrates the change in the weather patterns. It doesn't explain why the change has come about. That is, the causality, whether humans have actually caused this change. And nor does it tell us what will happen in future. That's the notably contentious part. And it certainly is contentious. We have a lot of stakeholders involved in climate change. I've just put some of them up here. I'm a hydrologist myself, but there are a lot of stakeholders, and they have different views. I could have added politicians in, and we'll come back to that in a minute. But the hostility that is catching almost in some of the statements that are made about climate change, I've just picked a couple of examples on here, and you can see, Aristotle, whoever Aristotle is, at the bottom here, talking about total UN bullshit. It's just another way to redistribute wealth from the developed world to the undeveloped world, and there's been no documented global warming for approximately 15 years. And there's another one up there. They're coming for your heating and air conditioning, it says. Somebody who feels that this is actually part of a power struggle. It's nothing to do with science at all. Donald Trump made some interesting comments on global warming too, and I'll come back to those right at the end, actually. It's a more or less relevant saga today, I think. He actually said he's going to be renegotiating the Paris climate change agreement because it's too damaging to the US coal industry. Now, in the interest of balance, though, I will show you 2 or 3 placards held up by other people on climate change marches. I like these. We are moderates, aren't we? I'm a little upset. This one's good. I'm so angry I made a sign. And now we have an even better one. My arms are tired. Protest, anyway, can take various forms. But whatever the situation is, feelings run high. And that's not unexpected, since the stakes are also very high. So I'll leave that one up for a minute. A recent study from Cambridge University's Judge School suggested that better information on climate temperature rise due to greenhouse gases, in fact, they wanted to halve, if we could halve, the current uncertainty range for mean temperature in 70 years' time. They say that could be worth, and I'm reading this carefully, $10.3 trillion if we could halve the uncertainty for the predictions for 70 years ahead. It's because people can, bet on the stock exchange more accurately. So the current uncertainty range we have for what temperatures might be like in 70 years' time is between about 1 and 3 degrees, something like that. And we'd need to take some action to reduce that as well, to be able to realise the savings. But however you do the calculations, there are huge amounts of money tied up in this. There are huge uncertainties as well. Now, in relation, and just to pick up one example of uncertainties, in the water environment, we often say that we've seen flooding. Flooding has increased. We all know flooding has increased, don't we? That's what we say. In fact, if we analyse the examples of water moving through British rivers or present in soil moisture, there isn't any evidence. Well, there is very limited evidence of that yet. There's a wonderful Met Office guru, Dame Julia Slingo, who talks about changes in the jet stream playing a hose pipe onto Cumbria last winter, which is, I think, a really nice analogy. And we tend to assume that those catastrophic changes, those catastrophic floods that we've seen in the last decade or so, are the result of increased frequencies of intense rainstorms, and that those are consistent with climate change, which of course they are. But we also know, and I'll show you some diagrams in a minute, that there have been phases of floods and droughts in the UK in the past not dissimilar to the ones we see today. So we're probably not yet, in terms of river flow in Britain, not beyond the typical range of variability that we've seen in the past. Now, that doesn't mean that we're not experiencing climate change, and I'll come back to that in a minute. But in fact, the greater part of the UK flooding problem is probably that we've made ourselves more vulnerable and less resilient by building on floodplains and by managing the land in catchments in an inappropriate way. So it's a very complex, multifaceted, and, if you like, a wicked problem, and some of you will have heard me talk about wicked problems before. Now, I will just emphasise, before I go any further, that I stand alongside I think it's now 97% of environmental scientists who believe that the evidence for human influence on the planet's climate through the generation of greenhouse gases is now overwhelming. Okay, so I'm actually firmly in that camp, but I'm going to show you some other evidence as well and some other thoughts. I don't make any claim that human activity is the only driver of shifts in climate patterns, and my research, such that it is not funded by any agency that has a direct financial interest in the outcomes either. Remember that $10.3 trillion. There's a lot of money at stake. What I will say, though, is that there are a lot of people arguing without strong basis in scientific facts. I see that particularly amongst climate change deniers, but I have to agree that the pro-campaigners have not been without their spin doctors too. There's an excellent book by Roger Pielke called The Climate Fix, and he tells a really good tale of the campaigners Al Gore and James Hansen trying to influence an American congressional hearing back in 1988. And they were making a case for climate change and something needing to be done. And they organised so that they presented the evidence on what was statistically the hottest day of the summer, and they sabotaged the air conditioning in the room beforehand. So, you know, there are problems on both sides, really. The testimony, actually, that was given, it got very widespread media coverage because the temperature and the tempers rose in the room. And there was some evidence from somebody called Fred Singer, who was he's one of the people who refused to accept the evidence on smoking having an influence on health. And he said that the carbon reduction programmes should be delayed while more evidence was collected. But that was met with quite a lot of scepticism as they all sweated, I think. That error, or if you like, a slanting of the situation, or indeed the lies that were being told, depending on your perspective, is also evident in Britain. Some of you will remember in 2009 the University of East Anglia's ClimateGate scandal. Do you remember that one? It was to do with evidence being presented, incorrect assertions being drawn from that without proper peer review. And that also gave the climate change deniers some extra ammunition. So, you know, there are faults on both sides. Overall, though, despite those rather sort of regrettable lapses in the presentation of evidence, I'm still convinced that climate change is happening and that human activity is part of the explanation. Now, I can only talk about a very limited number of themes today, and what I want to do, really, is to talk about the kind of changes in our understandings that have taken place very recently. So I'm going to move us on from pictures like this, which would have been generated, probably were this one, 20 or 30 years ago, let's say 20 years ago. I'm going to review the major influences and planetary scale impacts of climate change, and then look at these new, complex and emerging science of carbon circulation and the generation and losses of other greenhouse gases. So, as a result of investment in scientific research, we now know a great deal more than we did a decade ago. But even the introductory steps of modelling increasing greenhouse gases and sinks require a lot of interdisciplinary inputs. Remember the diagram I showed earlier. The problem is made even more challenging because the factors that influence temperature changes, such as ocean circulation and terrestrial ecosystem responses, will themselves be altered as the climate shifts. So if you warm things up, the ocean the waters may expand, or the vegetation may shift, and that has feedbacks into the system. There may be tipping points where a small change in one element of a system precipitates a catastrophic change in the system as a whole. Now, I'm just going to illustrate that, and you'll have to bear with me a minute, because I do have some props here. Let's see if I can avoid making a horrible, wetter mess than I'd anticipated. Here's the Earth, okay? I should have probably had a bigger one, but this is a small Earth. And I want you to imagine that this upturned waste paper basket is a system. It's an environmental system. And if we have our Earth sitting in an environmental system, sitting like this, it's very stable. Okay? It's not going anywhere. We have inputs of solar radiation, we have radiation going out, we have changes going on, but the thing is in balance, it's static. Now, in reality, the Earth is not like that. It's more like this. The system, it's moving around, it's changing its position, but it's, we hope, perhaps got a tendency to return towards the middle of the system. Okay? That we would call dynamic equilibrium. The system is balanced in dynamic equilibrium. So that one, it's stable. This one is dynamic equilibrium. We hope that the influences that push the Earth around tend to bring it back towards the centre. You're probably ahead of me on where I'm going with this, aren't you, given this? If we push too hard, we can see something disastrous is going to happen. In my case, the ball is going to fall into the glass of water, but it's going to go off the edge of the system, and we may get a catastrophic failure. We may re-establish something, maybe down here on the lectern. The system will re-establish itself in some different way, maybe with less vegetation, with more water, or without people, for example, because we've simply pushed the situation too far. Okay, now I want you to keep that in mind, because what we don't know, or what we certainly didn't know a few years ago, is where are the environmental limits? We didn't have any idea. We are starting now to be able to tease some of those out. And the one that I think is particularly interesting that's on this diagram is the relationship between, for example, sea ice and the atmosphere, because we are starting to feel that there may be tipping points in the amount of sea ice that is generated as icebergs and floats away in the sea and can create catastrophic change. Okay, now I'll come back to that later. I really ought to throw this out, but it's actually it was a present to me, so I won't do that. Okay, now we know, as I said, now a great deal more than we did a decade ago about environmental systems, but there are so many climate-sensitive factors to consider that we need to narrow down the range of possible environmental outcomes so that we know what specific problems we have to tackle. And in my lecture today, I'm going to look particularly at some water-related elements. I'm a hydrologist, as I said, but one of the reasons for that is the UNFCCC, one of the United Nations group, have concluded that water crises or water-related elements make up 90% of the impacts of climate change. So very, very significant, and that's why I'm going to pick that up. Indeed, the World Economic Forum, if we go into the realms of economics, has identified water crises as the greatest global risk for the next decade, so even in the short term. The OECD added to that. They've said that some 4 billion people could be experiencing water scarcity by 2050, and we like to think here, sitting in reasonably wet Britain, that won't be us. But of course, it could be. Okay, and then towards the end of the talk, I'll come back and look at ways to reduce or mitigate some of the chances of potentially dangerous future changes, and particularly some of the more unusual technologies that seem to have promise, and probably a few that don't. Now, We are, as I said, in the aftermath of reasonably successful negotiations in Paris, at least we were until yesterday probably, and we're seeing the ramping up of political activity and national legislation in the UK. The UK has been a world leader in this arena of dealing with climate change and indeed in contributing to the science. And in terms of the action we've taken, we were the first nation to pass a Climate Change Act in 2008. Though, in fact, I should say that I think other countries have now surpassed our efforts in some areas. And we've made some progress in other areas too. For example, recognising that the ecosystems and habitats that provide us with oxygen, clean water, food and other materials must be protected in the face of changes. Not because it's good stewardship, that's obviously true, but because we absolutely rely on them for life support. Now, we know that the regulators of the Earth's climate include a set of partly predictable influences. We know quite a lot now about incoming solar radiation, basically heat, if you like, from the sun, which is affected by wobbles in the Earth's orbit, by tilting, slight variations in tilting, by changes in solar activity, and so on. But there is a critical element which we have to bear in mind, which is the one that's here, called biogeochemical cycles. And this is the area of gas in the atmosphere, which gases which we call greenhouse gases. Now, again, I'm not going to spend a long time describing what greenhouse gases do, but suffice it to say that it's been on the news so many times over the last decade, I can't believe that most people wouldn't know what we mean here. But basically, those are gases which in sufficient concentrations in the atmosphere affect the Earth's ability to receive radiation to the surface, but more importantly, to re-radiate it back out. Now, the most important greenhouse gas, does anybody know what it is? No, it's not carbon dioxide, it's water vapour. And, of course, that's an area that we know actually quite a lot less than we do about the other gases which you all identified, greenhouse gases, carbon dioxide, and, in fact, methane, the two that are most important. Without water vapour, though, the Earth would be a very cold place indeed. But carbon dioxide and methane are, from a variety of sources, are also important greenhouse gases. There are some other things which affect the way in which heat is used as well. So land-air interactions, the biosphere, human intervention we've talked about here, but what's going on in the soil, ocean currents, for example, and this one here, here's the water vapour clouds, of course, which, again, we'll touch on it again in a minute. But let's look at some of this. You may be familiar with some of these diagrams. This is a really good one. This is yesterday, so you can't claim we're not up to date here. This is observations taken in Hawaii of greenhouse gas concentrations, and it's updated, I think, almost every day. You can find it yourself. It shows the annual cycle, these little goings up and down in carbon dioxide concentrations in the atmosphere. Mauna Loa is supposed to be sufficiently far away from industrialisation so it's not affected by direct emissions of carbon dioxide from, say, urban areas. But it's showing the annual cycle is probably a result of vegetation emission by photosynthesis, particularly in the northern hemisphere, which has the largest land mass. But you can see not only the annual cycle, but obviously the massive rise that's taken place since the diagram starts here in 1960, which is, I think, where the observations when the observations started as well. So we start off down here, we've got greenhouse gas concentrations or carbon dioxide concentrations of about 315 parts per million, and today you can see we're up here, we're past the 400 mark earlier this year, I think. So we're now around 410, I think it is, on this diagram. Okay, now, indeed, exactly where that carbon dioxide comes from, and the carbon in it particularly, and where it goes to, was not understood when this diagram or these analyses were first observed. But there nevertheless was concern about what appeared to be a rise. So we were down here, and I can remember when I was an undergraduate in the early, I shouldn't say this, should I, dear? I'm sure I don't look it, but in the early 1970s, being told that there was a lot of debate about whether this was real or there was something wrong with the instruments or whatever. However, it did precipitate the first meetings of what became known as the Intergovernmental Panel on Climate Change, and they began to draw in researchers and commission research. And we've now reached the IPCC 5th assessment, which was published in 2013. Now, this diagram here shows you roughly the stores and flows of carbon in the atmosphere and in vegetation and soils and the ocean. And you see here particularly this massive storage in the ocean here. Small amount in vegetation, small amount in soils, a bit more in soils than in vegetation actually, which is an interesting one. And we haven't got a figure of total carbon in the atmosphere, but what we can see is some net flux. So this means the amount net that's moving in a particular direction. So on the ground, we think, or when this diagram was produced, we think about 1.4 billion metric tons, actually, is a vast. There's a ton of carbon dioxide there in a balloon. This is billions of metric tons. We think about 1.4 billion metric tons is net going into soils and vegetation a year out of the atmosphere. And about 1.7 is going into the ocean. And you probably may be aware of the concern that we have there for coral reefs and so on, because it's making the ocean acidic. But we've got up here a big problem. Here's the problem. The 7.9 net from fossil fuels, land use, and so on, that's going out back into the atmosphere and contributing to atmospheric carbon dioxide. Now you can see when this diagram was done, it was about 360 parts per million, so it was done a while ago. And that's a good indication about our understanding a few years ago. Now, we now know a lot more about the questions we need to ask. So on the scales here, on the left, we've got the knowns. So we know, for example, that the Earth is likely to get hotter if carbon dioxide increases. We know that sea level will rise by some metres, probably. We know that there will be more droughts and floods. We know that other pollutants are cooling the Earth. Sulfates, for example, are cooling the Earth. Greenhouse gases we've talked about. We know that habitats will shift. I think this is unequivocal now. 97% of scientists would accept that this is the case. But we've got a lot of things on the unknown side here. For example, how far will the greenhouse gases rise? And that's a matter of political motivation in part. Can habitats and organisms maintain biodiversity if the climate is shifting? Can they keep up? Where does the heat go to? That's a very good question. If it's getting hotter, where is all the heat going to? How quickly will sea level rise? Exactly how much hotter will it get and where? Are there any tipping points? We talked about that before. And how large are our cooling effects that we might have now through pollution or that we could have in the future? Now, those are big questions, and they are questions where we now have more of the answer than we did 10 years ago. So if we started to look at emissions of carbon dioxide, for example, I put up this because it's a ghastly complicated diagram, but you get the idea, I hope, that there's still quite a lot of uncertainty in this. It's probably the biggest uncertainty. So here's historical emissions, just of the last few years, and here's all sorts of estimates that we might use for the purposes of forecasting. So we talk here about assemblages of different models forecasting different futures. A future here where the gigatons of carbon dioxide per year emissions was perhaps over 100, and one here where there was a net reduction. We're actually sucking carbon dioxide out of the air, and everything in between. So that's one of the biggest uncertainties. That most of the carbon is emitted, in fact, by China, the United States, and India, and you will be aware, I'm sure, that it's coming from the burning of coal, oil, and gas. And it's still going up. Of course, we're making lots of efforts to reduce it, but it is still going up. If we look at the relationship between greenhouse gases and measured temperatures in the recent past, we can start to build models of how it works. In very, very simple terms, we just project forward the greenhouse gas concentrations and we link it to the temperature. Okay, very, very simple. If we do that, we can find out about carbon dioxide concentrations in the past by finding bubbles of gas in glaciers and that kind of thing. We can tell quite a lot about the composition of the atmosphere from that. And we can start to reproduce models that show us what's happened over very long periods indeed. And this one I've shown you because this is one that precipitated quite a lot of controversy. This one was somebody who testified in the States, and he said current worldwide warming has happened before, and therefore it's not a problem. We don't need to worry about it. And he showed this diagram, which showed the Roman period, the medieval warm period, and the modern warm period with this rather sudden rise, I have to say. And you can see some of the data here coming from satellites and some a bit earlier from thermometers, of course. And here's this period known in the UK as the Little Ice Age, which actually was more or less global phenomenon. Okay, now, one of the things we don't know is more detail about the carbon dioxide and how it plays out around the world, because carbon dioxide concentrations are not, we now know, constant around the world. The atmosphere isn't all the same. So here we can see just from the last few years, from satellite imagery from 2003 to last year, we can see carbon dioxide, the red line here. This is the sort of latitude that Britain is at with this big annual variability in carbon dioxide concentrations. But if we go to the far south of the planet, New Zealand, that kind of latitude, the change, there's still the upward trend, but not the annual cycle. So we now know a lot more about the distribution of carbon dioxide in the atmosphere. Now, I put this up because I was going to show you this diagram, and I might start to think that there's some conspiracy going on here, because it was on the European Space Agency website. I've just come back from China, actually, or Tibet, yesterday, actually. And before I went, I checked that it was there. When I got back yesterday, it had gone. There was a very nice animation showing the growth in carbon dioxide. And I could be, cynical and say somebody's taken it down. But anyway, let's hope it comes back. But doesn't alter the fact that I can show you other diagrams. This one is showing you carbon dioxide. This one is for methane. We leave carbon dioxide from it. This is a methane map. And the yellower we have, the yellow or the redder, is where methane is levels of methane are being recorded, again from a satellite. Now, what you can see here is the satellite in the recordings in the southern hemisphere, low levels of methane. Don't worry about the units, but they're low levels of methane. In the middle latitudes here, we've got higher levels, and then we've got one or two areas here in India and Southeast Asia and parts of China where the levels are very high indeed. And the levels there are coming from paddy rice production. Okay, actually, I'm just interested. I was just about here. The day before yesterday. The grey is just because we haven't got the data. There's not enough data, so it's shaded grey. And there are small observations you can see here of red that might well indicate permafrost melting, as you say. I would say at the moment there's not quite enough data to be sure on that one. If we look at it very recently, we've got a map here that does attempt to do this in a bit more detail, and this at the top here we've got 2003, that's the sort of levels of methane emissions that we were seeing, and 2010 to 2011, some changes, a bit more here. and across Africa. So it's small, but it's probably increasing. And methane is a very powerful greenhouse gas. That's why it's attracted a lot of attention. And there's been a lot of debate about where it comes from. I like this one. This is the latest sort of thing that we can now do because we have so much data. We can produce simulations of what's happening. You can see at the bottom here, here's the levels of methane gas going up. And you can see what's happening here on the Earth. It's changing all the time, and the amount of information we have year by year is changing. But by and large, it's going redder. So methane levels are generally increasing as well. And of course, that's precipitated a lot of discussion about where it comes from. I love this one. Not me, surely, but it might be. And as people were accusing McDonald's, weren't they, not so long ago, of saying, well, it's all your fault, there's too many hamburgers, and that's causing a problem with methane. But the more research now showing you very large amounts of methane being released from reservoirs, which we didn't, I think, a few years ago we wouldn't have expected. So methane is bubbling up from the beds of reservoirs, which is very worrying because reservoirs are one of the ways in which we try to accommodate or adjust to climate change. Okay, now if we start to look at what's happening on to this heat, we can be pretty sure that most of that extra heat, if you like, 90% of it has been stored in the ocean. And it's virtually certain that the upper 700 metres of water has warmed since 1971. I think I've got a diagram of this in a minute. But I put this up. I'm actually doing a lecture on this. I can't remember if it's the next one or the one after that, on the oceans. But many of you will be aware, perhaps, that as well as there being a jet stream, which is the circulation of air, wind we experience this as wind, in the upper atmosphere, there's also this massive circulation of water in the oceans. So the little red thing we see here, this dotted line, that's the Gulf Stream that we all know about. It keeps the UK much warmer than its North American equivalent in terms of latitude. And if any of you have ever been to that part of Canada, you'd be pretty pleased you live in the UK, I think. It's very cold. So that's keeping us warmer. But there's this much larger circulation, global circulation of water, which actually manifests itself through differences in salinity and temperature. So there's a huge movement of water. It follows round a sort of complex circuit. So some of it goes like that, from the Atlantic into the Indian Ocean and back, and there's a sort of dividing point here south of Africa, and lots of it goes round into the Pacific and round there and then back and joins up somewhere in the Indian Ocean. So we've got this massive circulation of water, which is turning around and moving heat around. We've also got indications that heat is taken into the water and moved down through turbulence in the water. This is actually research from Plymouth University. And again, I won't go into the details, but they were looking at carbon and how it gets down from the surface deeper into the oceans. They were actually concerned with the organisms that grow there because that's what they have as food. But it enables us to get some sense of where carbon is coming from and going to within the ocean. So this is carbon, but heat is going to be very similar. Okay, now I'm going to move on a little bit to looking at the consequences of some of this. You can see here, we all see catastrophic reports in the newspapers about deserts and forests dying and polar bears starving and coral reefs dying, and here, on the left here, sea level rise. Now, those are good stories in the newspaper. Again, we have moved on quite a lot in the last few years in our understanding of how significant some of these things will be, and I can only touch on one or two of them. But this is the latest climate change, long-term climate change projections under bad circumstances, okay, if we don't do something about our emissions of carbon dioxide. So you can see here for the tail end of the current century that it's going to be hotter, probably in this case over 2 degrees hotter, at least in some of these northern parts, and again, hotter still a bit later on. So really complicated diagrams starting to emerge. Again, we don't have to go through all the details, but here's another example. They're forecasting, in this case, coldest daily and warmest daily temperatures and frost days and tropical nights when it's going to be very hot. Now, we can start to be a bit more certain now, because of the science and the research that's been done more recently, about these consequences. So some of these stories of catastrophe, if we do nothing, are not as far-fetched as people were making out in the first instance. We take this one. Conversely, we now know quite a lot more about how vegetation takes up carbon dioxide. Now, if you have a greenhouse, you'd be very well advised to come breathe heavily in it, because the raising of carbon dioxide levels will encourage your plants to grow more leafy, to be more leafy. I often think this is perhaps why the Prince of Wales does so well with his whatever it is, his plants. He talks to his plants, the carbon dioxide levels are raised, and in this case at planetary scale, the vegetated land has shown significant amounts of greening. Okay, so it's actually not desertification we're seeing here, it's greening for the most part. And most of that data has come from recent satellite images, and carbon dioxide fertilisation, the research suggests, explains about 70% of that greening effect. So some areas really are greening a lot. You can see up here in some of these northern areas. Okay, so we're finding out more. We also know a lot more about where the carbon is stored in the soil or the plants. So if we look at the red areas here, these are areas which are where there's a lot of organic matter stored in the dead organic matter. So it's in soil, okay? Hence the permafrost up here and the Alps and so on. And down here, the green and the yellows, we've got, or the green in particular, we've got more stored in the vegetation than in the soil. So there's a balance. We know more fine-tuning about the way the climate is influenced. We know more too about sea level change. Although if we go back to the 1960s, we'd already seen some changes. These are based on tidal records, or tidal gauges. We've seen some evidence that sea level had increased since the 1920s, but from the 1980s onwards, we've seen a very rapid rise in sea levels, and some indications that this is the start of glacial melt influencing sea level rise. The first observations of that are around here. This is a diagram of just a mock-up of what Florida might look like with, say, 6 metres of sea level rise. So the average rise is something like 4 or 5 millimetres a year, but it's actually very fast, faster than that in more recent years. So some of us who can remember the British shorelines might think, oh, is it going up that much? Well, in fact, we've had a further development since then, which is that what we've discovered now, the latest things, is that this is only published last month, that in some of the areas, if we look at the UK here, actually where the glacial melting has taken place, the sea level rise is not sea level is not going up as fast as we think it might be, and it's something to do with the way the ice moves away. And the recovery of the ground from the weight of the ice. So there are all sorts of issues there. So on balance, what the research that came out in 2016 said was actually we're underestimating sea level rise from that previous position there. We're actually really underestimating it. And part of it is because we put our tidal gauges in particular places that tend to show, not to show the greatest amounts of rise. But anyway, it's more complicated pattern than we might have thought. So again, something else we know. We know quite a lot about ice movement too, more than we did before. We know, for example, from satellite imagery from looking through glaciers. This is Greenland here. We know that these areas here in red are areas where the ice is not stuck to the bedrock, and here in the middle it is. So these areas here are probably not moving very fast, but these ones here in red are moving pretty quickly and are shedding ice into the ocean quickly. So again, we're fine-tuning the models. I'm going to skate over this one, but basically, of course, if you think back to my bucket and my earth, we're starting to think about whether there are these tipping points. And ice melt is one of the typical ones where there might be a tipping point fairly immediately. So if we get a sudden movement of ice, we'll likely get a sudden rise in sea level. Okay, and we now know a lot more about ecological zones as well. I love this cute little frog. Apparently he dies more easily when temperatures fluctuate up and down. And we know quite a lot more about the nature of biological resources in the face of climate change. Again, all of this is moved on very, very quickly in recent years. Just to bring it home, I just want to include a little bit on the water environment in the UK. A very interesting report came out again in September this year, which is the UK Flood Resilience Review, and it's available on the web. It's an interesting read for a number of reasons. Had a very distinguished set of contributors. Some people have alleged that this is a conspiracy, because what it concluded was that the UK's weather is very variable, and it's very difficult to detect changes in the behaviour of particular things like storminess. So what we see here is rainfall. It's actually winter rainfall in England and Wales, and you can see it's not really changing very much, gone up a little bit here, but there are drier periods and wetter periods. If we look at stream flow, the same period, we've got flood-rich and flood-poor periods, and some of you will remember some of those, I'm sure. There were some very large floods, of course, in the 18th and 19th centuries, and indeed earlier. If you put those two together, you start to think, well, there isn't much evidence that there's a change in river runoff, even though there might be a change in climate. And indeed, what the conspiracy theory is to say, well, that's the government commissioned this, therefore we don't have to spend any extra money on flood management. But it doesn't look really as if there is much change. But there are diagrams like this in there, and it's actually printed in the original in this rather fuzzy way. But here we are, here's the record. The grey area here is the sort of range we might expect typically. And here's some future scenarios for the UK from 2000 over to the next century. And if we have this blue scenario, it's likely it's going to go up like this, which will cause problems if you live in wherever it might be, Richmond or somewhere, and other areas too. So we are suggesting that in this case, precipitation might go up, but not yet that the influence is seen in runoff. Now, other people have disagreed with that. Just flagging that up, average annual flow has increased over the last 50 years in Scotland, Wales and parts of northern and western England, but no pronounced changes have occurred in the lowlands of southeast England. Where do the decision makers live, one might ask? And will they spend any money on flooding? Interesting question. And they do note that winter flows have increased in upland and western catchments. Okay, now, what can we do about it? Can we do anything about it? Well, we all know the conventional types of solutions, of course, these days. It wasn't conventional 20 years ago, but solar panels are pretty good. This is just near where the latest climate change talks are going on this week in Marrakesh. Huge solar arrays. Britain isn't doing too well on solar arrays. We're here. This is kilowatt hours per person per year being generated. And you might say, oh, well, it's not very sunny here. Actually, we seem to be putting most of our solar panels in around Sheffield when I looked at the figures on this for some mysterious reason. There's a very good salesman, evidently, in Sheffield. But we could do better, clearly. We are, though, getting pretty good at wind power in the UK. We're about to have the world's largest solar array, I think, off Grimsby, this Hornsea Project 2, which is the blue area on here, with 300 turbines. And that's, I think, likely to be effective. Hydropower, we're non-starters, even though the Queen has put her best endeavours into it and shown the way with a low gradient turbine on her estates in Windsor. But some areas are doing pretty well. Canada, as you see there, and even Russia are doing much better than we are. And of course, there's always the nuclear option. We appear to be about to invest in that, although of course the Germans don't, and there's a German protest about that. Okay. What else? Well, biofuels, they're a good thing, aren't they? Well, actually, the evidence suggests that they're not a good thing. At least the first generation biofuels, which are crops grown specifically to make fuel, the latest analysis, and again this has only occurred in the last few years, is showing that they probably produce more fossil fuel, more emissions than fossil fuels, at least a lot less than benefit than was originally suggested. And even there must be questions too about the so-called second generation ones here, which are using crop residues and waste, because of the amount of transport that you need to take this stuff around. And if we're using fossil fuels to transport it around, that's rather silly. Now, geoengineering. I'm just going to touch briefly on this because we don't have enough time to talk in detail about this. But and I love the diagram on the right, by the way, a little picture. This is dealing with the trouble in genuinely different ways. And I put this up because each one of these that we think about, each way, we have to think about the value of it, the risk, whether it's transparent, whether there are vested interests, or whether there are legal considerations. So let's take this one, for example. This is a general diagram that shows all sorts of geoengineering and novel solutions. So towers that spray water into the air, remember water vapour, clouds reflecting more energy. But of course, water vapour is also a greenhouse gas, so that's problematic. We might produce char. We might engineer deep-rooted crops that put carbon down further into the soil. We might liquefy carbon dioxide and put it into oil reservoirs. We might stuff spare carbon dioxide onto the seabed, and so it goes on. There are lots of possibilities. This one is just an example of clouds seeded by particles in ship exhaust in 2013. You can see ship exhaust, there's lots of cloud being precipitated. And the point about this is that people are saying we should be doing these experiments to see what happens. We should be doing it. And there's obviously some considerable risk attached to that. So if you precipitate, if you use a particular technique somewhere and it has some unfortunate consequences somewhere else, internationally perhaps, you may find yourself in difficulties. This is exactly what happened with cloud seeding experiments to try and influence rainfall. The biggest gain came for the lawyers, and people downwind suing the people upwind for stealing their rain. I'm sure we'll have the same issues with this. There are lots of different technologies. I'm not going to talk about all of them, but this one here is something you will have heard about, carbon capture and storage. We've just decided not to invest in this in the UK, or at least the government has decided not to invest. But it has very interesting side effects. Here's the carbon dioxide being captured by stacks from factories or power stations, carbon dioxide transported in a pipeline and pumped into various places. Now, one of the places it might be into a deep aquifer, but another place might be into an oil reservoir, where, of course, it helps you to get more oil out. so you can force the oil out, and that's called enhanced oil recovery. Now, you have to think about this in a systems term, and you have to think, well, is that really what we're trying to do here? And it may not be, of course. Biochar is a very local thing, by and large. It's about burning waste organic matter, and you can buy biochar in your local B&Q. I have to be equitable here and say, what would I say? Waitrose as well, probably. But you burn the organic matter in an environment without oxygen, and then you bury it. It's like charcoal, that's what it looks like, and it might be able to take maybe 12% of our emissions if we did enough of it. Okay? We can even, in some cases, contemplate direct capture of carbon dioxide from the air. So you pull with your car into a refueling station, which has been sucking carbon dioxide out of the air and turning it into fuel. Now, that is technically possible. But again, you can see where some of it's going into the oil reservoirs, and it's going to be refined, and it's making fuel. So there's fossil fuel, unless you can do this with renewable sources of energy, this air capture. That may not be the case, of course. So it's not something you can just do on its own. And here's another one, enhanced weathering. There are lots of materials that actually take up carbon dioxide in particular circumstances, and you can pile it up, and hopefully you can store it somewhere. I don't know how we would relate to large heaps of stored carbon dioxide over London, for example, but it probably would need using with caution. Okay, and there are various techniques for scrubbing carbon dioxide out of the air as well. Now, I'm going to draw this to a conclusion by saying that, in fact, none of these is really of the scale that we need, nowhere near the scale we need. We are going to be forced back on renewable energy sources and reducing our energy consumption, in my view. Most people, when they were polled around the world, agreed with that. Even East Asian countries, people in Vietnam and China and India, and so on, Indonesia, they thought that climate change was a problem, and they wanted something done about it, even if it was going to cost money. So, there is a whole issue here about what was agreed in Paris, which I touched on earlier, and I won't go through in detail, but there's an action gap, what we need to do and what we're actually doing. And I'm going to explore more of that in my next lecture in the series here, this idea about action gaps. We have something going on in our head which doesn't allow us to see or believe what some of the science is saying. And my very last slide, I think, there's a delightful irony. I mentioned Donald Trump, but if you look at the diagram I showed earlier on the right there, for the areas of Florida that would be recovered, they are preferentially Trump voting areas. So Florida carries 29 electoral college voters, I believe, so there would be a nice justice, wouldn't there, if it did happen and he was responsible for pulling out of the Paris Agreement. Don't quote me on that. Thank you very much, ladies and gentlemen.